In class, we are learning about Newton's second law, which states that an object's final velocity is equal to the object's initial velocity plus the total net forces acting on the object over the mass times delta t, the change in time. With Newton's second law, we are able to predict the position of an object of a short time delta t in the future. To do this, we need to first know the object's starting position, the average velocity, and the amount of time we're going to predict. Just by looking at this equation, we can see that when the total net force is zero, the object should be moving at a constant velocity of vi. Vi plus zero will just equal vi. To test our ability to predict an object's position in the future, I set up an experiment. I recorded an object moving at a constant velocity, then created a computer model to simulate the object moving at the constant velocity, and I compared the two. Here is the video I recorded. I then used the tracker to gain position versus time data. Here is the video. To create a model, there is necessary information you need to get. We need the initial position, velocity average, and the change in time. We get initial position from our first x component, which in my case was 0. To find the average velocity, all we need is to take 2 points. I took my first 2 points and my last 2 points. So I took delta x, the change in the position, over delta t, the change in time. Here is the math for finding the velocity average. My answer ends up being negative 0.9892, or you could express that as 0.9892 in the negative x direction. And since I started at time 0, I also have my delta t right here, 0.1667. Now I have all the information I need to create my computer model. I have the velocity average, initial position, and the change in time. To create our model, we now have to input all of our data. The first thing is the skateboard's mass, 2.0 kilograms. The initial starting position of the skateboard, which is the 0 vector, and our skateboard's constant velocity of 0.9892 in the negative x direction. We also have to initialize our starting time to 0. Another thing we have to initialize is the net force. We have to initialize it to 0, as that is the whole point of the experiment, that when there's no net force, our object will move at a constant velocity. We also must input our delta t into the while loop to make sure that our prediction model does not go past what we observed in real life. To make sure the physics works in our model, I inputted the fundamental principle of Newton's second law. I also input the equation to find the new position of the skateboard at each step of the while loop. Running the simulation looks like this. The blue ball representing the skateboard goes to the left, or the negative x direction, and we can see that this line goes down to about negative 1.6. Running the simulation gives you all the points that came from the chart, going all the way down to a final position of negative 1.62229. This is compared to our observed final position of negative 1.65. This is a graph with both lines plotted, the blue being the predicted and the orange being the observed. As you can see, these lines are pretty close, so my model was pretty accurate. You can also see that my prediction was slightly a little bit of an underprediction compared to my observed. What accounts for this is probably my choice in average velocity. I obtained these by taking my last points. Had I taken one of my earlier points, I believe that I would have overpredicted instead of underpredicted, since in the earlier times, external forces such as friction have not already acted upon the skateboard and slowed it down. Other questions still remain, like how does my choice of axes affect my outcome? My choice of axes made sure that all the direction was in the negative for x. Had I flipped them, I would have the same magnitude, yet on a different direction. These predictions can be made accurately by knowing that the net force is 0, but we can never know how many pushes or pulls are being acted on the object. Thank you.